Well, thank you everyone for joining us today. We're here to discuss edge computing, AI, cloud privacy, and cybersecurity, together with Hub Security's very own CTO and co-founder, Andrey Iaremenko, alongside confidential computing expert Stefano Tempesta from the Azure Confidential Computing product group at Microsoft. We're going to start our webinar today with a brief introduction from our speakers, followed by an introduction from Andrey on today's discussion topic. Afterwards, we'll open a bit of a deeper discussion on everything related to confidential computing and data privacy, including its ongoing threats and solutions. As usual, we'll leave about 30 minutes at the end of our discussion for a short Q&A. So if you have any questions throughout, feel free to drop them in the Q&A section below on the right side, and we'll get to them later on. I'm joined now by Stefano Tempesta. Hello, Stefano.
Hi, Shterny. Hello, everybody. Welcome to this session.
Thanks for being here. Maybe you can give us a quick introduction on yourself and what your field of expertise is.
Okay, yes, thank you. Well, first of all, thanks for having me in this conversation. I'm Stefano Tempesta. I'm based in Australia and I work at Microsoft in the Azure Confidential Computing product group. So essentially where we build confidential computing in the Microsoft Azure cloud. So my expertise are in all the aspects of cloud security and artificial intelligence as a broader extension. And I also sort of collaborate or as an advisor on a volunteer based on the national blockchain roadmap for the government here in Australia.
Great. Well, welcome. We're really glad that you could be here with us today. We're also joined by Andrey Iaremenko. Welcome, Andrey.
Hi, Shterny. Welcome, everyone. Great pleasure to join the webinars again. And also talk about the confidential compute topic, which is becoming hotter and more relevant every day, if not every hour, given the growing ability of hackers to go into every system, everywhere, anytime, and the information becoming more regulated and private and very, very sensitive and worth lots of money, basically. And it's a great moment to talk about it in this webinar, and also a real pleasure to have you, Stefano, with us as an expert in confidential compute.
Great, thank you, Andrey. Maybe you can give us a short introduction on yourself and your background.
Yeah, sure. So myself, as I'm a Hub Security CTO and co-founder, being here in the company for 3.5 years. Before this, my main background is from IDF and defense industry, doing more on offensive cyber applications development. So it's a very natural transformation from one side to another. So now using all the knowledge and experience to actually protect information and keep secrets for people and organizations.
Thank you so much, Andrey. So we're super glad you could be here with us today. And we've had many other webinars with you, so I'm looking forward to today's discussion. We're going to keep it a bit open-ended, so I'll throw some questions out. Feel free to jump in, either Andrey or Stefano, whoever wants to respond. But we'll start off with a very basic question, which is, maybe one of you can give us a very brief intro to confidential computing. What is it? And in very simple terms, how does it work?
All right, I'll try to give it a first definition in some way. There is a very specific use case for confidential computing, which is protection of data when it is in use, when it is in memory. If you think for a moment, we already have a protection or encryption of data at rest when it is stored in a file system, in a database, in some sort of storage. And we also have already protection of data in motion or in transit when it's moving over the internet, for example, HTTPS, right? So the data is encrypted already there. So already our data and our applications are secure. Whether in any cloud provider, data is safe. But there is a moment when this data is taken out of where it is stored and it is running in a server, in a virtual machine, in a container, which is actually in memory. If someone intentionally or not take a memory dump of that memory, of that virtual machine, they can actually see your data, even if it was encrypted at rest. This is where confidential computing makes a difference by protecting that memory space using hardware execution environments, so hardware protected execution environments that prevent the access to this memory space.
Great. Andrey, anything to add to that?
Yeah, so it's a great explanation. And I only want to add to this that in addition, I think, to data, which is private and secret, also we are seeing today applications like the binary code of the application that is using the data in the same memory or on the same machine, also becoming an asset, which needs to keep secret and private. For example, AI models during inferencing or training, which parameters and the model code is as sensitive and secret as the data itself that it's handles, basically. And also in confidential compute, for example, talking about the same AI application space, hardware plays a part, as if the application runs on several processing units, for example, the CPU and the GPU together, a single application. So the confidentiality of the data and the code needs to be need to encompass both processors, which makes the confidential compute more broader perspective, more interesting, and also much more complex to define the boundary and to protect against attackers.
Right. And we hear about many different approaches to confidential computing, including novel cutting-edge mathematics, such as homomorphic encryption. Maybe you could clarify for our audience what some of these approaches are.
Look, from my experience, confidential computing has a variety of different approaches. One is actually the homomorphic encryption that you mentioned, which is not a different algorithm of encryption. But if you look into the word homomorphic, it means the same form, the same shape. So data is being accessed in the same shape that it is, which is encrypted. So typically, when we encrypt some data, we use a symmetric or asymmetric key for encryption, using all public and private keys. There are several algorithms for doing that, and it requires data to be transferred from one party to another one, and the receiving party needs to decrypt that data to access, to use it. With homomorphic encryption, you can use data as it is, in the same format as it is, so without decryption. And this is end-to-end encryption. So it's basically data that is encrypted and is never decrypted, and it can be used in encrypted format, even when it is in memory. So it is a form of confidential computing, but it is done with software computation. It is not based on hardware encryption as for the other approaches that are based on Intel SGX enclaves or AMD secure environment modules.
So maybe to add to this, I think that the form classification can be, is it really a software-based method or a hardware-based method? And there are different hardware approaches. So they start with you can One can encrypt and only portions of application code or portions of the data lifecycle when it is used. If we take, for example, ARM secure enclaves, which are very specific, very focused on keeping simple cryptography and keys and maybe data safe. And then there are AMD secure enclave, which encrypts the whole virtual machine in place in memory without changing anything in the software stack of the application or operating system. And both of them are hardware-based approaches, and they're based on the main CPU, main processor that the client, the system already using. And the other hardware approach can be what is called HSM, hardware security module, which is taking all the secrets, if it's the data and if it's an application, and putting them on a separate hardware, which is physically isolated and runs the sensitive computations and sensitive data completely separated from the main CPU. And this is a different approach, much more costly, and in many cases less feasible. For example, in first-tier cloud providers like Microsoft or Google or Amazon. And of course, all the software approaches like homomorphic encryption, which is the cutting edge of making secure private computation using software only in any environment.
And the need for confidential computing in the cloud seems obvious, but what about on the edge?
Hey, good question. Confidential computing is based on hardware encryption. So anywhere you have hardware, like as I mentioned, Intel SGX or AMD SEB, which is able to run on premises or at the edge, it doesn't have to be a cloud provider. You can still have confidential computing. So actually, the ideal world, so it's sort of my vision, no, in where I want confidential computing to evolve, is to have a full confidential cloud and edge, end-to-end confidentiality on premises, at the edge, and in the cloud. So the edge is definitely I don't know, it is a space, it is an environment, it is a section that we need to protect. Think of medical devices that run inside the hospital, for example. They capture imaginaries or they capture patient data, and it may not be synced in real time with the confidential cloud, no? So with a hub for storing this information in the cloud itself. They may reside in the device for some time. And then you have a technician that is doing some maintenance or some patching update on the device itself. Well, the technician potentially can access this sensitive patient data on the device itself until it is erased, until it's moved out of the device and transferred to the server. That is a need for confidentiality at the edge.
Anything else to add to that, Andrey?
Yeah, so I think maybe even the first question is what is an edge? And if we look 5 years from now or 10 years from now, I think the definition or distinction between the data center or center and the edge will become irrelevant, as we are seeing this this already starting today as the compute move from the data centers, from the servers in centralized locations and to the local small servers or even boxes outdoor and outdoor installations. And the AI operations are moving to the smartphones, are moving to the into the smart cars, and like everything is becoming hyper connected. So, for example, if you take a cellular network, so the thing which nobody, like we all use, and but we don't see it as normal users. looking at the propagation from GSM second generation into the 5G that we have today, the cellular network infrastructure over which a huge amount of data comes through today is completely flat, IP-based standard network, and everything is connected from the base station at the front on the tower, on the cell tower, and up to the internet provider and the central processing of all the traffic. Everything is on the same network. Everything is connected, and applications are moving and from the centralized data centers to the towers, and also vice versa. Things that have been done at the front are now done at the data center because it's more efficient to do so, for example. So maybe to talk about the edge, as Stefano mentioned, is maybe we need to talk about confidential compute as a whole, as one single thing, without distinction between edge and data center, because everything will be single cloud basically. And definitely confidential compute is needed everywhere there is a secret to keep. That's the main thing. You have a secret data, you have a secret application, you have something that you don't want to be hacked, disturbed, or changed, or falsified. You need confidential compute.
So can organizations run confidential workloads on premises, or do they need to be in a public cloud?
You can run on premises. Either approach. The hardware approach requires that you have the necessary hardware, like Intel SGX, AMD SEV, or the homomorphic encryption approach will still be valid as long as the organization is able to run this software encryption. It doesn't have to be a cloud provider. It doesn't have to be any of the big cloud providers. It can be also another regional one, as long as it is based on these hardware CPUs, then you are able to run confidential computing on premises. Shterny, do you want to address some of the questions from the audience now that are relevant to this conversation? Because I see that some people are asking about homomorphic encryption.
Sure. I was going to just ask you that. We have a question here from Joseph. He asks, can you comment on the level of security for hardware versus software-based methods for confidential computing? Maybe
yes, good point. Look, at the end, it all goes down to where you put your trust. You put your trust into hardware, into a hardware manufacturer. You put your trust into a software, into an algorithm, into whoever has developed the algorithm. Software are typically easier to tamper with than hardware. Hardware will require some physical access. There have been situations also where hardware can be compromised also without physical answer, but it's very, very limited situation. Probably we are not in a position to compare the two and say one is more secure than the other one, simply because the adoption is much different. Homomorphic encryption, although being incredibly brilliant as a technology, is still not mature enough for broad application, mostly because of the performance of it. The software-based encryption requires a computation capability that is, as you can appreciate, more intense than having a hardware-based encryption. So we don't have workloads that are using homomorphic encryption at scale, that can compare to a hardware-based trusted execution environment. So to make it simple, the majority of organizations at the moment are choosing the approach of hardware-based protection rather than the software-based protection. So it's very difficult to say one is more secure or the other one, because organizations are choosing one over the other one. They're choosing because the technology is more mature in one side over the other one, because cloud providers are offering one solution over the other one. So I can speak of Microsoft. We are offering hardware-based trusted execution environment, although at Microsoft, we also have a research project on homomorphic encryption, but it is still a research project. It's not commercial level yet. I don't know, Andrey, if you have a different perspective or a different experience on which one is more secure or the other one. But for me, it's very hard to say, oh, hardware is more secure. It is because more clients are using it. But more clients are using it because it's more available in the market than homomorphic encryption.
So it's more to complement your answer, Stefano. It's like basically like every other thing in cybersecurity, or choosing what is the most secure solution is depends on the use case, depends on the specific requirements and specific environments of the application, the data, and their business workflow. So it's the Intel SGX, the homomorphic encryption, the hardware security modules, they are all tools. Each one has advantages and disadvantages. Each one has its own problems and its own solutions. For example, like homomorphic encryption, it's really very slow today. It's huge yes. And very complicated computations. So, and they can only run on standard CPUs. You cannot use GPU today to run homomorphic encryption computations. So it's not acceleratable, basically. That's why DARPA, for example, have today a research project to create chips which are ASICs geared toward the homomorphic encryption acceleration. It's so hard to do this. But however, it is suitable, for example, for text processing, for low intensity, low throughput data, and then it creates a very good solution for complete privacy end-to-end for an application that runs on the cloud. That's one example. On the other end, there is a hardware-based secure enclaves using standard CPUs, and all of them have been shown to have vulnerabilities over time. Some of them are being patched, some of them are open or cannot be patched. AMD is one of the examples, one of the recent examples, I think, that published a vulnerability in their secure VM flow implementation. So it's a toolbox, and for each specific application, the use case, you need to choose the right tool for the job, which is makes sense from business perspective and from regulation perspective for the specific client.
As a follow-up question to that, sorry, Stefano, did you want to add on to that?
Yeah, no, look, I want to say that the two technologies are not competing to each other. This is actually the position of the Confidential Computing Consortium. So there is a consortium that Microsoft is a co-founder, and there are several other organizations that are hardware manufacturer and software manufacturer, and they all contribute to create a sort of standards of definition of confidential computing. So it's called C3 or CCC, or Confidential Computing Consortium. And there is Intel, there is Microsoft, there is there are different organizations that are also purely software oriented. And although Confidential Computing Consortium currently support a few open source projects that leverage Intel SGX mainly, then the hardware-based approach is sort of how can I say, a supplement, to the homomorphic encryption. The two technologies are not in competition. They have different applications, and as Andrey said, depends on the use case, what you are looking for, and when you can apply.
As a follow-up to that, and we have another question from Joseph, which is, how do the different software or hardware techniques meet scalability needs? Are there advantages over one over another in this regard, or is it pretty much the same answer? It just depends on the use case.
Andrey, maybe you want to take this because you already answered before. Homomorphic encryption at the moment is slower and too slow for practical use. So the scalability you can only reach with hardware, but maybe you want to confirm this.
So I can start, and then it's also, I think, depends on. So first of all, for this homomorphic encryption, definitely it's not scalable today. Even for big data centers using standard servers, standard CPUs. And from the hardware perspective, basically everywhere you have a relevant CPU, CPU-based secure enclave, it's an ARM processor or x86 processor, you can put this specific implementation of confidential compute. So looking on the all the PCs and servers in the world, in data centers or private installations, private hosting clouds, the CPU-based confidential compute approach is scalable almost infinitely. Everywhere you have the relevant CPU, and it's very pervasive today, you can use this confidential compute solution. So maybe Stefano, you can add from your knowledge, like internal knowledge of how Microsoft are like deploying it, and what are the scalability of Intel secure enclaves.
So look, there is a customer that I'm happy to mention because is an open source non-profit organization, which is Signal, the messenger app. They are using confidential computing for protecting the social graph, so the contact list. So all your contacts are stored inside a trusted execution environment, inside an enclave. In this way, no one can access this contact list, not even people at Signal organization, so the engineers. It means that this contact cannot be used for targeting ads or for selling to other organizations, right? So it's protection of your contact list. And they scale because now they have millions and millions of users and thousands and thousands of cores of running confidential computing. So it is possible to scale, and this is the approach that you will need to take at the moment, using Intel SGX or AMD SEV as soon as the technology is more available for larger audience.
Distributed multi-cloud compute, right? This is a growing need today that we're seeing in organizations.
Totally. Absolutely.
There's many solutions for it, but with the solutions come security challenges. Would you guys mind expanding on some of them, and what they are when organizations start expanding outside of the single data center cloud provider boundaries?
Yeah, I mean, it all goes down to making sure that data remains confidential when crossing boundaries within the same data center, within the same cloud provider, and obviously even more when you're crossing in a multi-cloud or cross-cloud environment. This is something that probably a few people, I don't know, maybe neglect or don't consider properly in their design. One typical use case that I can mention now, for example, is key protection. So your keys, your secrets to access a database or an API, these sort of things. You typically want to use a key management solution. And because this is a best practice, right? So you protect your keys, your secrets, your certificates into a vault. And a key management solution provides you a secure environment for protecting your keys, your secrets. Now, there is a challenge though, and that is when you take the key out of the vault and you start using in your application, and then maybe the key is necessary to access a microservice on one side or a database on the other side, or you call a cognitive service, or you run or you decrypt some data. So you start using inside your same environment, or even across different data centers, across different cloud providers, because maybe you are consuming an API from a third party, which is not hosted in the same environment that you are running your application, right? So it's a very diverse configuration. Well, the problem is that key, once it's taken out of the vault and is being used by the application that is running your machine learning or consuming the API, whatever that is again in memory. And if someone has access to that memory in the moment that the key is being used to access the API, to decrypt the database, to decrypt the file, the decryption key is compromised. So you need to be sure that even when using key management, secret management, and when you, especially when you're going towards external services on other data centers, on other cloud providers, that your secrets are still inside the hardware secure module. So they are still inside the enclave. And because once they leave the enclave and they are in memory, I'm sorry, they're gone. I mean, they're not gone, but potentially can be compromised.
We're coming up on it's our final 20 minutes, and I want to leave some time for Q&A. We can go 15 minutes over our scheduled end time, if that's okay for you, Stefano and Andrey.
Sure.
But I want to maybe get to some of these questions that are pouring into the chat. Somebody here, Rita asks, does it make it easier to use data safely in collaboration and a trusted data sharing approach?
Does it make it easier to use data safely in collaboration, a trusted data sharing approach? Well, if I understand the question, collaboration, data sharing is the multi-party computing is the use case for confidential computing. When you have multiple parties that are accessing this data and you don't want all the parties to have access to this data, but only one centralized application that runs inside the enclave, that's the best use for use case for CC, for confidential computing. So we call it multi-party computing or multi-party machine learning, because one typical application is when your machine learning needs to operate on an aggregation of different data sets coming from different data sources. And the larger the data set in use for training your model, the more accurate is the prediction of machine learning. So this case of data sharing or aggregation from multiple parties is definitely a use case for confidential computing.
And maybe to add to this, this question actually touches on very important part of distributed confidential compute, like collaboration, data collaboration, or AI collaboration, which is access control. So the data is encrypted and it is inside the secure enclaves all the time. However, in collaboration, it's usually also regulated and the data must be kept private in between the parties. So the access control layer above the computational layer is extremely important in this case to ensure privacy and secrecy and safety of the collaboration.
All right, we have another question here from Joseph. Is there any industry best practice or guidance on combinations or configurations of encryption at rest, in transit, and during processing or analysis, such as within an SGX enclave?
Well, maybe I can start and Stefano can add on specific on SGX. So generally speaking, on about the data in transit or data in storage, so the best practices are to use the most recent encryption algorithms and authentication algorithms. For example, the most recent TLS protocol version, and using AES-256, which is proven to be, which is not unbreakable until now. So that's data in transit and data at rest. So use the latest things, use the most current software implementations of cryptography algorithms until you get into the secure enclave, for example, like Intel SGX.
Yeah, look, I'll be very, very short. The best practice is do all of them. Encryption at rest, in transit, in use. If you want to have the end-to-end protection, the three areas has to be protected. You can't just do protection in memory and then not protect the rest. And it's typical to do protection and rest and in motion, but not in memory, and that's okay if you don't have sensitive data that can be compromised. So that's absolutely fine. But if you want to the utmost protection, the three of them go together.
Definitely.
Great, thank you. We have another question here from Mohammed. So the Confidential Computing Consortium defines a trusted execution environment. Well, let's see if I understood this correctly. A trusted execution environment, or TEE, is commonly defined as an environment that provides a level of assurance of data integrity, data confidentiality, and code integrity. What is your perspective on this definition? Specifically, how can a trusted execution environment be of any use without any attestation guarantees to the end user? Don't you think that attestation is critical feature of TEE?
Yes, attestation, it is critical. Attestation is about making sure that the code is running inside an enclave that is genuine and is based on one of the CPUs that have this unique signature, unique key for encryption. So before establishing a communication with an enclave, you want to have, and you have to have an attestation that makes sure that the code is not being compromised, the enclave is genuine, and the communication can be established.
Andrey, did you want to add something to that?
Not to this one.
Okay. Another question here is data de-identification better than confidential computing and encryption? What do you guys, what's your take on that? So Andrey, I guess.
Yeah, sure. So the data de-identification, it's like a partial thing, which is not even a solution to confidentiality, is like removing the user data or identity data, for example, from a picture or from a location. Today, it's quite easy to bring back the identity from the anonymized data using a huge amount of personal data available on the internet and data stolen from organizations, institutions, and available on the black market for sale. So somebody who wants to know who you are or know where the data came from, today it's quite easy to do based only on the anonymous data. So it's not really a solution to confidentiality anymore.
I've heard that Intel STX is not that secure after all, and that vulnerabilities have actually been detected. Any thoughts on this, Stefano?
Yeah, there are a lot of legends on the internet about that. Some may be true, some are a little bit exaggerated. And some can be actually exploited only if you have a physical hardware. So that means breaking in a data center, figuring out which one of the thousands and thousands of servers is running Intel SGX, and then finding the actual server and compromising the CPU. So, well, if you do that, congratulations, probably you deserve it, right? So it's very, very hard. Said that, there have been situations where there are some articles mentioning vulnerabilities on SGX, and some that Intel itself has acknowledged and fixed. So very briefly, one is, yes, when there is a vulnerability, as anything, as any software, any hardware requires some patching, and Intel is on top of that, and they can fix it, they could fix it and apply the fix, and Microsoft and Intel works very closely to make sure that these fixes are rolled out in the offering that we do to customer. The other one is, which was a little bit harder to fix, was on different threads that have access to cache data. So basically the problem is that data is cached, and then different threads access that cache, could potentially access confidential data inside the cache that is used by another thread. So to minimize the risk, in Azure, we have disabled hyper-threading on the virtual machines that run Intel SGX. So there is no risk for mixing up on the different threads and have access to data that is in one environment, protected from one enclave and the other one. Or the third and final approach is use a dedicated host. A dedicated host is basically running the entire VM confidential SGX only for you, and there is no risk for anybody else to have access to your data using hyper-threading vulnerabilities. But look, at the end, there is no solution for 100% perfection on security. We are trying to make it harder to access data and to reduce the surface attack. So there is a level of extra protection that this technology provides to make it more difficult to access data by unauthorized parties. It may not be perfect, but it's definitely much harder than not having it all, right?
Where do you see, oh, Andrey, did you want to add to that?
So maybe to add to this, actually based on the caching example, I want to generalize the answer. There is an inherent problem or vulnerability for any CPU-based or AMD implementation where the same CPU and the same microcode and the same registers, the same silicon processes the sensitive data from the memory enclave, and also all the regular data from the OS and all the normal applications that are running on the system. There's always going to be a problem when the same registers can need to switch from one data to another. And to get real true security, there is always needs to be a physical separation of execution. Because when we're talking about data in memory, it's also data inside the CPU, internal memory, registers, cache, and everything else, which is also needs to be isolated and kept secret. And in the standard CPUs, this is not the case, today at least. So that's in general answer to CPU-based secure enclaves.
We have another question here. What is your thoughts about SGX versus TDX approach? Which one do you think to have? Which one do you think to have the most prominent future aspect in terms of adaptability, reliability, and performance for legacy applications? I don't know if I read it right or if it was written. No, I think it was.
Yeah, this question makes sense. It is a good question. The TDX approach is comparable to some extent to the approach that AMD has already taken with the SEV SNP technology in protecting access to the entire VM rather than just a memory space inside the VM. And the difference is that when you want to access a memory space, an enclave, you need to have some coding techniques using some frameworks to make the communication with the memory space possible. With the approach with the entire VM being protected, the traditional lift and shift of legacy application is much easier because you just move the entire application into the VM and is automatically protected. So it's definitely a technology that makes it easier to protect your legacy application, but it comes also with a shortcoming in terms of protection, because anybody that has access to that VM can be someone inside your organization, then can access data that is running in data and code that is running inside the VM. So the enclave is the most control. So you have control and you have protection from other parties, from VM administrators, and from the cloud provider. The TDX or the current AMD approach, so TDX is not commercial available yet, but other approach where you protect the entire VM, you have protection from the cloud provider, so no one at Microsoft will ever see your data, and that's okay, but someone inside your organization could, because they have access to the VM. So again, depends on the use case that you want to take into consideration.
And where do you guys see confidential computing being in, let's say, 5 years from now?
What do you think, Andrey?
That's a great question. I think the intuitive answer, I don't know, or maybe nobody knows. This security, cybersecurity, and the compute space is developing extremely fast, and there is lots of innovation today, and it will only grow in the future. And we need to 5 years from now, it is actually very exciting because we can look on all the parallel technologies, for example, quantum computers, or quantum key distribution networks, quantum internet infrastructure that is being developed today. So maybe not 5, maybe 10 years from now, the tools that we have today will be only like intro tools or simple tools relative to what we'll have 5 or 10 years from now, where with the new novel technologies or things that haven't been invented yet. But generally speaking, I think in 5 years from now, we probably be able for every human being, everyone and everything that generates information, will be able to keep it private for the whole life cycle. So keep the ownership of this information from generation to deletion or storage, and also to control the access and control the distribution. So that's about confidential computing in the future.
Yeah, totally agree. And for me, it's really about creating a confidential experience end-to-end, cloud, edge, and on-premises also. Why not? This is all about putting the security first together, and then offering this service at scale. not just some niche users, some very specialized workloads, but anybody, government, for example. I would love to have digital identities issued by governments protected on confidential computing. I would like to see cryptocurrency or trading in general of any transaction, of any digital asset protected with confidential computing, because there is so much scam, there is so much hackering out there, and so much value that if we are able to protect transaction and identities, we are able to build a more confidential society at the end.
Definitely. So I think we're running a bit out of time, so I'm going to ask a final question for Andrey, and I'm going to tie it into a question that we've received from an audience member as well. So Gabor is asking, I have a question on the relative positioning of HSM, or hardware security modules, and confidential computing. Some HSM models allow the user to upload custom executable code. This use case seems quite clear to TEE, such as CPU-based confidential computing. Any thoughts on whether HSMs with custom module complements competes with confidential computing, and what is the advantage of confidential computing over HSM with a custom code?
Yeah, so look, is a great question that will require probably too long to answer. So I invite Gabor to get in touch so we can address this more in detail. The short answer for everybody's benefit is that, again, they're not competitive technology. HSM requires the use of dedicated hardware for protecting. Confidential computing takes the approach of CPU or generic hardware. So it's not really one is best, one is worse. It's more about one is easier and mainstream. The other one is more dedicated. They're both secure. They're both available, and they cost differently, right? So there are too many factors to give, and I don't have the context here for the specific use case to give a right answer. Unfortunately, I have to answer, it depends. So the conversation can be a bit longer than that.
Definitely. And I wanted to lead that into my question to Andrew. Maybe you can briefly summarize for us what Hub Security is doing to solve some of these security challenges that come with confidential computing.
Okay, thank you, Shterny. And I think the previous question leads also to this one. HSM keeps your keys and encrypts and digitally signs data. That's basically it. It cannot run applications, especially virtual machines and Dockers and very complicated applications. So it's a very specialized machine. At Hub Security, what we are doing, we're looking at the confidentiality as in a broad sense. And our vision is to enable anybody and anything, any organization, to keep secrets whenever they are, wherever they are. So in other words, Hub Security enables for the secret, for the application, if it's an AI, if it's a blockchain application, a financial application, keys and files and data, to still be able to remain at the same location, at the same server, on the same operating system. And by adding our solutions into the existing system, wherever it is, we provide a confidential enclave from any standard PC, any standard server, even if it doesn't have by itself any secure enclave internally. So Hub Security creates a wrapper around it that controls the access, controls the management, controls the information that comes in and out of this compute environment or compute device. And in this way, we basically create a confidential, confidential compute secure enclave from anything that is currently out there on the market as compute device, from the base station to the edge IoT devices, and all the way into high-end data center servers. And it's really tied to look in confidential compute as for the whole life cycle. Who has access to the information, where the keys that encrypt this information are kept, how the identification happening, how's the information shared for the whole way end to end.
Great. Well, with that, thank you everyone for a wonderful discussion. These are all super fascinating topics related to emerging security challenges, and I'm really glad that we got the time to cover them today together. And thank you to our speakers, Andrey Iaremenko and Stefano Tempesta. We hope that you're all staying safe and healthy at home, and we look forward to hosting many more discussions like these. If you'd like to get in touch with any of today's panelists, so feel free to reach out to them directly. All of today's attendees will be receiving an email in the coming days with the contact information for each of our panelists. So don't be afraid to reach out, drop them a line if you have any further questions on today's topics. And to stay up to date on upcoming webinars, you can follow Hub Security on LinkedIn and on Twitter. We also have a Medium where we publish the latest stories coming out of the cybersecurity and crypto sphere. So feel free to follow us there. And I'd like to thank our speakers one more time for joining us today.
Thanks for having us,
Thank
Shterny,
you.
and everybody.
My pleasure. Looking forward to another great discussion. Take care, everybody.